telling the folks that were here on time. If you need a good movie to go see, Unsung Heroes, very nice. One of the best I've seen in a while. So I didn't know anything about it going in. I didn't want to know anything about it. I had heard it was good. I'm like, I'm going to go in blind. I don't want to read reviews. I don't want to look at a trailer and see what it's. I didn't even see a trailer. Just went and saw the movie and loved it. Great, great film. So for those of you needing something to do for the weekend or something, go find Unsung Hero. All right. Well, I think we're going to go ahead and start. Everybody's here. It's going to be here for now, and others wandering late. They can play catch up. All right, third hour. Here we go. Let's go to our grade screen as usual. Scroll all the way down here. Ooh, we're down at the bottom. I got to open up some more lessons or something here. We're at graphing sequences and series. So we've studied arithmetic sequences and series. We've studied geometric sequences and series. Now we're going to learn about graphing these sequences and series. And that will finish up this module. I guess we'll be testing over it next week because I don't see any more lessons. I need to open that test up. All right, now let's close that right here. Oh, we have the part 1 and part 2 instructions, but the test is not there yet. Here's the lesson for graphing. All right, information at your fingertips. In today's always online world, news and data travel faster than ever, right? Something happens around the world, we know it very, very quickly. Information has become increasingly valuable. It's important to be able to decipher and communicate data in different formats. Infographics fill the internet because display data graphically can help others see the patterns, get the connections, the big picture of it all. So graphing a sequence or series can serve the same purpose. So we're going to learn about the key features that are unique to graphs of sequences and series, and how can the average rate of change be found using a discrete graph, because these are going to be discrete graphs. That doesn't mean we're not going to tell anyone about them. It just means mathematically they're discrete. All right, I'll look at restrictions. All right, when you learned about arithmetic and geometric sequences and series, we learned how the domains had specific restrictions. And you remember what they are? Well, I'll click this little tab if you don't remember. Remember, the domain was restricted to all integers. Integers, that means no decimal numbers, no halves, greater than or equal to 1. Remember, because the domain was the term number, first term, second term, third term, fourth term. Those are all integers, 1, 2, 3, 4. There's no 0th term. There's no negative third term. There's no 2.5 term. Integers only, greater than or equal to 1. So this exists because the domain represents the number of the term in the order of the sequence. Only the natural numbers are used. 1, 2, 3, etc. Decimals, fractions, and negative numbers are not included. Even 0 is admitted because you can have a term in the 0th place. So we already know that about graphing. We know graphing will have a domain restriction. What about the range? Well, the range has little or no restrictions. It just depends on the sequence or series you're graphing. Right? It represents the value of the terms in the sequence. And it could be any number. If our sequence has negative numbers, it'll be a negative graph. If it's positive, if it has both, like the geometric sequences that had positive and negative numbers, it could be anywhere. But you need to look at the situation you're giving, because the range can have restrictions based on the individual sequence or series. If the range represented the number of ostrich eggs, then it would be restricted to positive integers, just like the domain. We couldn't have negative 23.27 ostrich eggs. We could have 0, though, so it would have something different than the domain. It could have 0 ostrich eggs. All right, let's talk about that discrete term we saw. Discrete versus continuous. Those are opposites. So due to the limits of the domain, graphs of sequences and series are called discrete graphs. That means they only exist at specific values. That's not like a linear graph or an exponential function or parabola, because those are all continuous, right? It's you put your pencil down, you draw the entire graph without picking your pencil up, because you can make a continuous line. That's not true with discrete graphs. They only exist at certain values. Let's take a look. The graph on the left is a discrete graph. It only exists at the values of x that are integers. It only exists at 1 and 2 and 3 and 4 and 5. It does not exist anywhere between 4 and 5. Where a continuous graph, like this linear graph, all those values included 4.01, 4.2, 4.333333, 4.5, 4.81, all those values between 4 and 5 are there. And between every number, it's continuous, discrete, 4, 5, nothing in between. Now, when graphing a sequence, it's important to note where it's going to show up. You may want to resize or move the viewing window, because if we just use this graph and our sequence is all negative numbers, it won't show up in that graph, right? So that just makes sense. We modify our graph based on the data we're trying to show. But we'll slide the graphs only to the positive x-axis. We are still limited to 1 and larger on the domain, so we would not need to go to the areas 2 and 3, right? When we have our graph numbered 1, 2, 3, 4. So we would stay out of the second and third quadrant and just be in the first and fourth. All right, investigate whether the graphing program or calculator choice will accept a sequence, like Desmos. You can search for sequence with the help or support section. If it does accept a sequence, note how you should do that. So let's do that and see what Desmos says about graphing a sequence. So let's go to hit the little question mark, help center, graphing a sequence. Let's see. Is there anything that specifically talks about? What's the first thing it talks about? A recursive, depends on one more sequence. Yeah. Okay. Okay. With Desmos, we do it with a table. It can graph the table. So that's how we'll do that with the sequence, because we can display it in different ways. So if we make a table, hit the little plus button and say table, right? And we say our first term, second term, third term, fourth term, fifth term. And our first term is 0 and 2 and 4 and 6 and 8. That's the arithmetic sequence. And notice it graphs it as a discrete graph. It did not connect them. So graphing in Desmos, you just hit the plus button and add a table and fill in the values of your sequence or series. So there it is, a nice discrete graph, not connected because it doesn't exist between x equals 1 and x equals 2. And I'm gonna show those 1s and 2s. I like changing those settings. 1, 2, 3, 4, 5. There we go. So we can do that in Desmos. So we've investigated that. Then it says, if you're not sure, you could graph points. We could put 1, 1 and 2, 3 and 3, 5. Like if we wanted to add the next one that's 6, 10, we could say graph the point 6, 10. Say it graphed it in red because I put it on a different line. So we could enter every point individually if you want, or we could put it in a table so much quicker and easier. You can do it either way in Desmos. All right, the average rate of change can be calculated. Use the slope formula. So if you want to know the average rate of change between n equals 2 and n equals 4, you've got at 2 it equals 10 and at 4 it equals 40. When you graph that, here's the slope formula. y2 minus y1 equals x2 minus x1. 40 minus 10, because that's what the y values are. 40 minus 10 divided by 4 minus 2. So that's 30 divided by 2. The average rate of change is 15. For every 1, it goes up. The y value goes up 15. That's the common difference on an arithmetic sequence. We know that. All right, let's look at page 3 here. Graphing an arithmetic sequence. Okay. Bart has been keeping track of people who say they're coming to his birthday party next week. He got 3 replies on the first day, and since then he's gotten 5 more every day than the day before. So every day he's getting 5 more and 5 more. So create the explicit equation that determines the number of responses he gets and then graph it. So this is arithmetic because it's plus 5 every day. Every day he gets 5 more than anyone got before. So we got 3, and then the next day he gets 8, and the next day he gets 13. And obviously he's invited a lot of people. It doesn't say 5 times as many or 1/5. This is an add, plus 5, 5 more. So our sequence would be A sub n equals A1 plus the difference times n minus 1. So you can substitute it in with the numbers we know. The first day he got 3, so that's what A1 is equal to. And every day he gets 5 more. And they went ahead and distributed that to make it 5n minus 5, and then combined the 3 and the negative 2. So it equals 5n minus 2. Right? So you could put that on a graph, and it would be like that, 5n minus 2. Let's see what we can do in Desmos. If we make y 5n minus 2, try defining, oh yeah, we have here would say n. There we go. Let me take off this one here. So I put in n and 5n minus 2. So in the first term, it equals 3. On the second term, it equals 8. The third term, it equals 13. 4 equals 18 with a table. And look, it graphed it for us. There's our graph. By the 5th day, he got 23 invitations back. So you can do that in Desmos real nicely by using the table. I could use X if I want to. X, I just got to make sure they're both say X, same graph, X and 5X minus 2. But you can use n's like the sequences use. So theirs is just a different scale. Ours is going up faster just because of the scale. I can make ours look like theirs by saying, let's do our graph from -2 to 12. Did I do that right? The x-axis. Oh, -2 to 12, step 1. And make the y bigger so it goes up to 50. So you can make it less slanted, less steep, just depending on what scale you put for the x and y. Theirs goes from 0 to 8 and 0 to 50. So, but do not connect the dots. All right, let's see the other example they give up here. Mandy took some stale bread down to the pond to feed the ducks. The first day she went, there were 4 ducks. News was spreading, though, among the duck community because the next day there were 11 ducks. And then there were 18 ducks. She's gotten concerned she won't bring enough bread. So they want to graph the first 8 terms. Good question. Let's see if we can help Mandy figure out a graph for that. So we know that the first term, the first day, there were 4 ducks. And we know the second day was 11, next was 8. So we know it's a plus 7. So let's take a look at writing an equation for that. So they went a sub 8 equals the first day was 4 plus 7 and n minus 1, 7. Well, we want to leave the n minus 1 because we want an equation to graph. We're not trying to figure out what the 8th term is. N minus 1. So the equation would be 4 times 7n minus 7. 7n, 4 minus 7. So let's see if the graph of 7n minus 3 will give us what we want in Desmos. So let's take this back to an n, and we're going to do 7n minus 3. Now let's zoom in. All right, I got to change this again. I want to go by ones. First day, there were 4 ducks. The second day, there was 11 ducks. The third day, there were 18 ducks. So this works. 25 ducks. The first 8 terms, it said. We need to continue our table. There's the first 8 terms. There's 53 ducks show up on day 8. Adding 7. So we graphed the arithmetic sequence. Here's theirs. 7n minus 3 is how we simplified it. We did the first term plus the common difference times n minus 1. And then we simplified it to 7n minus 3. And there's the same graph that we got. Do not connect the dots. I can't say that enough. Every year I get people turn this assignment in with a line. And it's like, it's not a line. We didn't have day 2.6 where 14.3 ducks showed up, because that would have grossed Mandy out and she would have ran home screaming. All right, let's look at a geometric sequence. So Wyatt earns 80 points on a recent project. His instructor allows him to earn 1/10 of a point by doing some revisions. 1/10 of the points earned. So Wyatt can resubmit his project 9 times. Each time he gets an extra 1/10 of the points he earned on the submission before. So 1/10 of 80, that means he can get 8 points if he resubmits it. Right? And each time it'll just be 1/10 of it. Create an explicit equation that determines the points of where he earns a sub n and graph the sequence. So a n equals a1 r n minus 1. So when they substitute it in, they substitute 80 as the first term. That's what we had there. And then 1/10, that's 0.1 as the common ratio. So let's see what it looks like. A1 is 80, and that's 0.1 raised to the n minus 1. So let's put this in our table instead. So instead of 7n minus 3, it's going to be 80 times 0.1 raised to the power of, what did we raise it to? N minus 1. I'll put that in parentheses so it all goes as that. All right, there it is. We got to scroll out a little bit to see it all, because the first one's at 80. Then you can earn 8 points a second time. Then you can earn 0.8 points, and then 0.08 points, and then 0.008 points. At some point, I don't think it's worth turning this in 9 times, because it said you can resubmit it 9 times. By the 9th time, you're really, well, it's so small, it's even giving me a 0, but it's not a 0. It's just got a whole bunch of zeros in front of it. It's like 0.0000008. But there's what the graph would look like. Let's compare that to what they did. Yeah, see, same thing they did. 80, 8, 0.8, 0.08, 0.008, 0.008, and it gets smaller and smaller. All right, second example. Each year that Zoe leaves her money in a savings account, it's 103% larger, which means she still has 100%, and she gained 3 more. 103%. She initially put in $1,500. So graph for 7 years. All right, so she put in, let's see, $1,500. That's our A1. And it gains 3%, or it has 1.03 every year. 1.03 n minus 1. So we have to scroll way out to see this, because we're starting at 1,500. There it is. 1,500. And the next year, it's got 1,545 because it gained 3%. And then it went to 1,591.35, and then 1,639. So it's gaining a little bit more than $45 every year after that. We can see that. It looks like a straight line just because our X's aren't very great. We got, this is 1,700, but that's only 6 on the X. See what their graph looks like. They spread theirs out a bit. Oh, well, theirs is wrong. They started with 100. They started with 150 instead of 1,500. See, their graph is wrong. They said 150, but up here it's 1,500. They forgot a 0. So we win. Just kidding. Just kidding. All right. Let's go to see what's on the next page. Oh, scroll back up. Page 4. This should be the last page of the lesson. Yep, there's the lesson summary. All right. That was all sequences. Let's talk about graphing a series. Right? The arithmetic series formula, S sub n equals n divided by 2. 2 times the first term plus the common difference n minus 1. The geometric was S of n equals a1 minus a1 times r to the n over 1 minus r. Should have those in your notes from the past couple of weeks. Why these formulas and not the ones with an a sub n? Because the independent variable is needed to be able to graph a series, but the sum formulas, that's not used. You're using the r. That's where we're using that. So, all right, let's see. Example 1, Bart has been keeping track of people who say they're coming to his birthday party. He got 3 replies in the first day. Since then, he's got 5 more. So this is what we were looking at before, but now we're going to look at the sums. So we figure how many total invitations has he received? Not just that he got 3 this day, 8 this day, 13 this day. He needs to know the total number of people coming. So using the arithmetic series formula, which is this one right here, and substituting in what we know, let's see, S sub n equals n divided by 2, 2 times the first term. First term is 3. 5 was the common difference, times n minus 1. So 2 times 3 is 6. 5 times n minus 1 is 5n minus 5. So they can just put it in just like this. We could simplify that if we wanted to, multiply the n through there and all this. But that's fine. Let's just put it straight like this into Desmos. Take that out. And we're putting n divided by 2 times, let's see what that was, 5n plus 1. So what it ended up? Yeah, 5n plus 1. Okay, so this, we need to zoom out again because we need to go back way back down here. All right, let's see. Let's change our scale here again too, but step by one, the y's will go from -1, x's will go from -1. See the x's, let's go to 10, and the y's, let's go to 80, something like that. All right. So the first day, he's got 3 invitations back. The second day, he got 8 more, so he's got 11. Now he's got 24 because he got 13 in that third day. And then he gets 18 in, and now he's got 42 people coming, and it just keeps going up. I don't know that it told us when to stop, but the 9th day is 207. 207 people coming by the 9th day, if it goes that far. But this doesn't say how many days we looked at. They went 8 days. So they were about where we were. 8 days, we had 164, which is where they were right there, 164. So we can do the same thing just by taking this formula. Over here is the geometric, where it's 80 points, and we do the 1/10 thing. So using that formula, it's a little more complicated, but we can still put that into Desmos. 80 minus 80 times 0.1 to the n. All right, so on top of our fraction, let's put all this together. 80 minus 80 times, see, and that was 0.1 to the n. 0.1 to the n. And that's all on top. So we'll close our parentheses there. And it's divided by, see, if we put all that in parentheses, it'll put all of that as the numerator. 0.9, 0.9, 0.9. So there it is. He starts out with the 80 points. Then he gains 8 points the first time he turns it in. And then he gains 0.8. Then he gains 0.08 and 0.08. He just keeps getting more and more 8s. But he'll never get it to an 89 unless the professor rounds up. If we start with an 80, he can get up to almost an 89. It'll be repeating 8s the more it goes, as you see in the table. And see, the graph looks just like our graph did. So that graph looks, that's what their graph looks like. All right, lesson summary. Restrictions to the range and domain, that's the biggest thing. Remember, the x's start at 1, and we do not connect it. These are discrete graphs, so they only exist at those points, not at the area in between. Do not connect it. So this is really what you need in your notes. To graph arithmetic sequences, you use that formula. Geometric sequences, use that formula. And you can type that directly into Desmos in the table, just like I did there, substituting in what you know. You know A sub 1. You know what the D is. You know what the R is. So you have to substitute those numbers in. N should be the only variable you have. That stays an N. Everything else, substitute in the numbers. And then if you need to find the average rate of change between 2 points, use the average rate of change slope formula, y2 minus y1, x2 minus x1. They have a page of practice problems. If you want to try graphing some before you get to the assignment, here it is. Graph the first 6 terms of a sequence where it starts with -3 and the common difference is 4. I love it. Every time I highlight it, it puts it in another line. Check your work. There you can see if your graph looks like this graph. It gives you the actual points. So you should be able to verify that you end up with those points. And it gives you the equation over there in case you couldn't figure it out. 6 of those problems exist. There's 6 of them. This one gives it to you in a table, right? So you can check. It gives you the formula you should have used. 6 of those. All right, let's look at the assignment that goes with this week's lesson. Calculate the average rate of change from n equals 1 to n equals 5. So from this point, 1, 2, to 5, 14, what is the common difference? That's what the average rate of change is. How much is it going up each time? What's the average rate of change? Is it 2, 3, 4, or 9? What's the average rate of change for this geometric sequence from 1 to 3? Take the first point and the third point, use that slope formula. It tells you what is equal to. It's equal to 8. Here it's equal to 2. The x went up 2, the y went up 6. Graph the first 6 terms of a sequence where the first term is -10 and has a common difference of 3. So which one of these 4 graphs is correct? Wow. I was just saying wow because they made it really, really easy. Because when I look at that, only one of those graphs has a first term that's -10. I don't even have to look at the difference. I don't have to look at the slope because there's only one of them that they got the first term right. If your A1's not -10, that can't be the graph. All right, number 4, graph the first 6 terms where the first term is 4 and the common ratio is 2, so it doubles every time. Which one of these graphs starts out with the first term of 4 and doubles every time? And I'll tell you again, only one of those graphs has the first term of 4. They're making it really easy on you. Graph the 6 terms of a finite sequence where the first term is 5, common difference is 1.25. All right. There you go. There's your assignment. 5 questions. They made the graphs pretty easy because most of them they're so different they can't be the same thing. There you go. That's all we got. This is testing week. Some of you may be Atlas testing. Seniors are work key testing. Freshmen and sophomore Atlas testing. So all kinds of crazy stuff. So I don't think I'll be here Wednesday because I think I have to be a hall monitor for some of that. I'm work keys testing with people on Tuesday. We got all kinds. It's a busy testing week. You know how that is. So anyway, get this assignment done quickly. If you're behind anything, get that done because May is Wednesday. And this is a B-Day Friday. So if you have questions, email me. We'll find a time to get together and get your questions answered. But otherwise, have a great week. We'll see ya.